Alright, so in this video we're going to solve problem 685 in Hibbeler. So again, another beam problem. This one's a little different. You have this beam here that's loaded in the following manner. Supported here, you can assume this is basically pinned at B, and then it's explicitly pinned at A. And then the cross-section is given to you as a width B and then a height, which is 1.5 times the width. You're given an allowable stress. So you're saying that the stress in the beam cannot exceed 10 megapascals. And it asks you to basically design the beam. Find B, this dimension, such that the allowable stress does not exceed 10 megapascals. Okay. Okay. So again, well, this is a little different. It's a design problem. So the first thing, again, we still always have to do is get the bending moment. Then the second step is going to be to knowing that the stress is equal to the max bending moment C over I, and if we define C over I as 1 over S the shape factor, where the shape factor is I over C, and we set the stress, the maximum stress, to the allowable stress, we can basically solve for the shape factor is equal to the maximum bending moment over the allowable stress. Okay? Now that we know S, we can then design the geometry, I'll say it that way. Alright? So we don't necessarily know the geometry, but we know the shape factor S. Okay. In this problem, it's relatively simple because they give you the height as a function of the width of the beam. Often both of them you're free to choose, so you have two variables that you can choose, really one relationship, so you have two parameters, one relationship. It becomes really more of an optimization problem, all right, so let's do the first step. Let's find out the bending moment diagrams. So first, to do that, we need to compute the reaction forces. So we'll put a force at A and the reaction force at B. All right. To do that, we invoke equilibrium on the entire beam. So here's the free body diagram of the total beam. FB, FA, and then we can make the equivalent point force of this distributed load. So it's 500 Newton meters over 2 meters, so it's a 1,000 Newton force acting downward, and it would occur at half the distance, or 1 meter, right? So we can put that on here. This distance here is the 1 meter. This distance here is 4 meters. Okay, let's do sum of moments around this point, around A. That'll give me FB. So the 1,000 is a negative 1,000 Newton times 1 meter, so that's the moment. And then FB, it's a positive FB, it's a positive moment, and its moment arm is 4 meters. That has to go to 0, so that tells me that FB is 1,000 Newton meters over 4 meters, which is 250 newtons. So this is 250 newtons acting upward, and then we do sum of forces in the y, have to go to 0, so that tells me FA has to equal 1,000 newtons, the downward force, minus 250 newtons, the force up at B. And that equals 750 newtons. So this is 750 newtons. Okay, so this now we have the external reaction forces. Now we can compute the bending moment diagram. Let's first look at this section between x. Well, we'll draw the x-axis this way, okay, and this is the y-axis. So let's consider x between 2 and 4 meters. So that's this section of the beam. We'll look at a little arbitrary cross-section there. What do you have? Well, you just have the 250 newtons acting upward. Then we have the internal reaction bending moment and the shear force. So if we do sum of moments around this point, what you get is, oh, I'm sorry, this distance here is x, and so this distance to this point is 4 meters. So this distance here is 4 meters minus x. So the internal reaction moment, here's a negative, equals 250 newtons times 4 meters minus x. So that's the equation. So it's a linear function. So it vanishes at this point. Here's x. Here's the moment. Here's 2 meters. Here's 4 meters. So it starts off at 0. The moment vanishes at this point. And then it increases. Well, it's a decreasing function because it has a slope of minus 250. And the slope here is 250 until we get to this point, right? At this point, the bending moment should be 500 Newton meters, right? Because it's occurring, goes over the 250, and it starts at 0, and it's over 2 meters. So 2 times 250 is 500. All right. Now, what happens at this point? Well, we draw that free body diagram between 0 and 2, and well, let me draw it. This is kind of like a little bit more like a graphical approach. Normally I would have done the left-hand side, but since we already kind of did the right-hand side part, let's keep doing that. So again, we have the 250 newtons acting up, but now we have this distributed force acting down. Put that in green just to show, because we're going to equivalence that with a point force. So there's the downward force. All right. Then we're going to have the internal reaction moment and shear. Again, we're not really that concerned about the reaction shear, but we're most concerned about the moment. Again, the distance up to this point here is x, so that means that this distance here is going to be the length of the beam minus x, or that's 4 meters minus x. Now, this distance to this point is 2 meters, right? Up to this point is 2 meters, so that means this distance here is 2 meters minus x. Okay? So the total downward force, the effective downward force of this distributed load, it's going to occur right here at 2 meters minus x on 2, and its magnitude is going to be 500 Newton meters over 2 meters minus x that it acts on. All right. So this 250 is still going to exist, and it's still going to have the same exact form. So actually, you can imagine this goes up. Now we basically just have to add the moment due to this guy. Now it's going to be a negative moment. So this one, that distributed load, is going to produce a negative 500 Newton meters times 2 meters minus x over its moment arm, which is the 2 meters, 2 minus x on 2. So we get this over 2. So this is really going to be minus 250 Newton meters, 2 meters minus x quantity squared. So this is a parabolic function, all right? I know from looking at this that the moment has to vanish at point A because there's no external moment there and it's not supported. And it's quadratic, okay? So it's quadratic such that if you were just to look at this part, we basically would have something that kind of looks like this. Right? This is the moment quadratic coming from this distributed load. It starts here and then it increases. Well, it should decrease because it's a negative moment, okay? And I know this is the inflection point because if I look at the derivative of this, right? The derivative of this would give me minus 500 2 minus x, okay? Actually, minus 1, so it becomes a positive. That's the derivative of this moment function. So you can see that actually the slope of that curve at x equal to 2 is 0. So this is, it's a quadratic function here. Right? So if we look at this, we know it's going to go to 0 at this point. So these are going to cancel out. You could calculate it. You'll see it's the same. And right here, if we were to put this, we're adding to it something like this, that basically has to go down equally as much. So I actually should draw it a little more like that. When you add these two together, you're going to see you're going to start going up a little bit and then come down quadratically. So in fact, when you add these two together, this might not be the maximum. It might be such that the maximum point is somewhere in here. Okay? So how do we get that maximal point? The point where there's the maximum bending moment. Well, we write out the analytical function for the moment and then find the extrema points, just taking the derivative and finding where the derivative is equal to 0. So the moment in that section, between 0 and 2, the internal bending moment is going to be the portion from this point load. That is the 250 4 minus x minus the part from the distributed bending load, which is the minus 250 2 minus x quantity squared. Okay? So to find the maximal point, we want to take the derivative, which is equal to minus 250x minus 500, let me get a plus 500, 2 minus x. And we're going to set that equal to 0. And that'll be either a maximum or minimum point. So what do we have here? We have, rewriting this, I've got 1,000 minus 250 minus 500, so it's minus 750x. We want to get that to 0, so that tells me that x is equal to 1,000 over 750, which is 4/3 or 1.5 meters. So that's where the maximum stress occurs. Well, I should say at this point it's a max or a min. I suspect it's going to be a max. So it occurs coming in here, 1.5 meters. All right? So it's not right at the 2. It's because you get this little quadratic bubble. All right, that's good. We know where it is. We need to figure out what that max bending moment is. So we just substitute the 1.5 back into here. So we get the bending moment at 1.5. This becomes 250. 4 minus 1.5 is 2.5, right? 2.5, 3, 4. Minus 250 times 0.5 squared, and this becomes 562.5, and the units would be Newton meters. I kind of dropped the units here, but everything's in Newton meters. So, and so you can see that that is in fact greater than the stress at this point. So this is the maximal stress. Oops, you can't see that, can you? So you can see that it actually does go up from this point to the 563 Newton meters. To worry about significant digits, right? 3 significant digits. Okay, so now I know the maximum bending moment. All right, that's step one. Now we need to do the design. Okay, so basically at that point, at this 1.5 meters in, we need to design the beam such that the stress does not exceed that. So that's going to be the max. I always do because it begins with M. Moment max, right? So, right, which is going to be the 563 times C over I, right? And now I define this as S, so this gives me M max over S. So whenever we're doing the design problem, right, these are the geometric parameters. So I lump them into this one shape factor, S. I know the sigma allowable is 10 megapascals, so this tells me that the shape factor for the beam has to be that maximum bending moment, the 620, the 563, over the maximum allowable stress. So here we have 563 Newton meters over 10 megapascals. 10 times 10 to the 6th pascals. And so this will give me the answer in meters to the 4th. So this is, well, I could have done this in my head. Okay. It's 56.2 times 10 to the minus 6 meters to the 4th. Okay? So that's the shape factor. Fine. Well, I need to design it. I know the shape factor is, in fact, I over C. And in this particular design, we're limited to a rectangular cross-section. It's like a wood beam. And we're told that the base is B and the height has to be such that this is 1.5 times B. Now, I, in this case, is the base, B, times the height, which is 1.5 B cubed over 12. Now we divide that by C. C is going to be, it's symmetric, so the neutral actually goes right through the middle. So the C is going to be 0.75 times B. It's the same top and bottom. So C is 0.75 B, or I guess to keep the fractions, right, that would be 3/4 B. Well, I guess I get the decimals anyway. So that gives me S is in fact equal to, here I have 1.5 cubed B cubed over 12 divided by C, which is a 4/3 B, right? That's 1 on C. The B will cancel out with one of these and gives me a squared. This 4 will drop with this guy and make that a 3. And now I have, let's put a number in here because 1.5 cubed is annoying. So this gives me 0.375 or 3/16 B squared. All right? So since we're stuck with this section, S is 0.375 B squared. So now I know S from the allowable stress equation, the flexure equation basically. Set these two equal, right? And solve for B. So we know that 0.375 B squared has to equal 56.2 times 10 to the minus 6th meters to the fourth. And I should have units on this. This 0.375 comes about, it's going to be, that's a meter squared here, right? So I divide by 0.375 meters squared. This gives me B squared equals 0.15 times 10 to the minus third meters squared. Take the square root, and this gives me B is equal to 1.22 times 10 to the minus 2 meters, or that is 12.2 millimeters. Okay? All right. So that's B. Now, I kind of added this little caveat. Imagine that the beam cross sections are such that they're only in 5 millimeter increments. So you have to design B to the nearest 5 millimeter. Actually, it doesn't ask that in the text, but let's just make it more of a design problem, because usually your beams kind of come in standard sizes, and I don't know exactly what the spacing is on metric beams, but let's say it's 5 millimeters. All right. So that means, in fact, that should we round down or round up? Well, in this case, we want the stress not to exceed, so that means you want to use the more conservative estimate, or in fact, if we make S bigger, make the cross-section bigger, then the stress will drop. So in that situation, right, the nearest 5 millimeters would round this. You got a 5, 10, 15 millimeters. Okay, so B should be 15 millimeters. Okay, and that would be the answer.